Hi guys, we are on 4E. We're at the top of page 91. I've gone ahead and written a little of this in there so that I don't waste as much time trying to write and talk at the same time. We're going to continue talking about functions. We know in order to be a function, you have to have no repeating inputs. The inputs have to pair to a unique output. And we're going to talk about some specific kind of functions today, which are called linear functions. I know you can see the root word line in the word linear, so we are talking about straight lines to be linear functions, but they also have to be non-vertical. And we'll talk a little bit more about the special situation of vertical lines. Actually, we're going to be talking a lot about that in the weeks to come. So your linear function is a straight line that's not vertical, and it also has a constant rate of change. And we'll look at that when we look at these tables down here in just a minute. So quickly, we've just got a few little graphs that are sketched, no particular point shown on here, but from the graph, we ought to be able to tell whether it's a linear function or not and explain it. So yes, this guy is a linear function. He is a straight line, or part of one. He is going up by a constant rate, and he is a function because each x has a unique y. So if you were to plot these points, or some of these points, you would see that x, for every x, you have a unique y. No x repeats with a different y. Obviously, the second one's not a linear function because there's nothing linear about it. It's a curve. The third one is, again, a linear function. It's going from high to low, but it is a linear function. And as is this one. This one is a little bit of a special case. It's horizontal. But if you think about the points, some of the points on this line, and you were to actually list the ordered pairs, you would see that there is no x that repeats. The y repeats, but that was okay. The x does not repeat. And finally, the last example, this is a vertical line. He does not pass our definition. Our definition says it has to be non-vertical, right here. And this guy is the definition of vertical. And if you were to list a few of his points, you would see that you only have one x. It's 5. 5, 0, 5, 1, 5, 2, 5, 3, on and on and on. The x repeats several different times, many different times, with a different y. So that, by definition, is not a function, much less a linear function. So let's go down to a couple of these examples in example 2 and see what we've got. They're asking us to do a number of different things. They're asking us to graph our table, and if it is linear, write in words what the pattern is, and then finally write an equation that will start with y equals. So if I inspect this table, and I look at the table before I ever even plot the points, I notice that each one of my y values increase by 3. Y starts at 2 when x is 0, and this is important. But to get to the very next value, it's increased by 3, and then by 3 again, and by 3 again. And this pattern would continue if we enlarged our table. So in words, I can say as x increases by 1 unit, y increases by 3 units. So for every x that goes up by 1, y goes up 3 times as much. So if you look at the graph, come down here and look at the graph. I've got to be able to get rid of this guy. I've gone ahead and graphed it, and notice that I've done something with my intervals, which I usually do. I will inspect my table before I write my intervals, and I need to see that I need to get all the way to 11 or beyond on my y-axis. I don't have enough points to go up by 1, so I'm going to go up by 2s. I'm going to make my intervals such that my graph will fit, my points will fit. The x-axis I can leave as single units, 1, 2, 3, dot, 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 because I've got plenty of room to get to where I need to be on the x-axis. So here's my graph. And now the last part of this is writing the equation. So this is always how I start. I say y equals, and I want to know where is y when x is 0. When I have no zeros, where is y? He is at 2. That's my constant. And then the pattern says, for every single x that I have, every time at X value, you go up by 3 times that amount. So the equation would say 2 plus y is equal to 2 plus 3 times x. And you can satisfy yourself that this is correct by plugging in 1 for x. Do you get 5? 2 plus 3, yeah. 2 for x, 2 plus 6, 8, and so forth and so forth. Again, I start with y equals where it is when there are no x's, when x is 0. Where is y? He starts right there, constant. And then what happens to him? He goes up by 3 for every time that the x goes up by 1. So that's how I begin to write my equations. Let's look at this, this example over here real quick. I went ahead and plotted him so you wouldn't be subjected to my terrible graphing with this pen. Doesn't look all that great, but we're going to go with it. Again, I labeled my x and my y axis with different intervals so I could show all the points. And when I did that, I came up with a curve. So this guy is not linear. He is not a linear function. His rate of change is not constant. You can see he goes down by 1 here, down here, he goes down by 3, from here to here, he goes down by 5. Nothing constant about that. So this example B is not linear, and he does not have a constant rate of change. Okay, I'll come back and do some more examples in the next video. Bye.